and his PhD in image processing in 2011, both from the Technical University of Catalonia in Barcelona. From 2006 to 2011, he held a research assistant position in the image and video processing group of UBC, where he developed new algorithms for efficient 3D reconstruction for multi-camera settings, leading to real-time demo which can be visited in the UBC premises. In September 2011, he joined Technicolor Research and Invention in Hanover, where he holds a senior researcher position in the image processing lab. So, please.
Thank you for the introduction. So this is a work that we developed together with my colleagues Axel and Kochale and Malte Borsum. As you can see, it's a work on super resolution, which is intended to be used in new systems for interactive video navigation. The outline of the presentation is the one you can see here. I will first introduce the necessity for using super resolution in our system. I will explain a little bit of the theoretical demo, why we can proceed in this manner, and then I will introduce some details of the method and some experimental results. So in our lab, we are working on new systems for interactive visual experiences, which go beyond high definition and ultra high definition, and also beyond the capabilities of video. And well, one such application is a virtual camera that can be completely controlled by the user, and you can navigate freely to such a panoramic video stream like the one you can see here. One problem and one limitation of the perceived quality that we have is, as you can see here, the lack of resolution when you zoom into the scene and you want to get very close to the scene. Therefore, well, it's clear that we need to enhance the resolution even if the capture system doesn't provide it, and well, this is what we are intending to do with applying super resolution. I will very briefly make a taxonomy, a very general taxonomy about super resolution methods. There are the reconstruction-based super resolution methods. Those were the first approaches that appeared in the literature. Well, the basic idea is to model the imaging process and try to reverse it. For that, you need to have several captures that you can combine. And basically, you are relying on the presence of aliasing in the input images. However, such a family of methods is strongly limited by numerical stability problems, and the maximum feasible resolution gain is around 1.6. It's a theoretical limit, so it's actually quite limiting. On the other hand, there are the so-called example-based super resolution methods that were introduced by the computer graphics community, and well, the nice thing about them is that they are exploiting all the knowledge that we have about the images that we are trying to upscale, and this allows us to obtain larger upscaling factors, up to 8 times, something like that. And well, another nice feature is that it doesn't rely or it doesn't depend on the presence of aliasing in the input images, which actually happens seldomly, and it's usually well something that undesired. I mean, correctly set up camera shouldn't include so much of this. Well, so we are interested in making single image super resolution, and what we are going to exploit is a feature that occurs in natural images, which is called cross-scale subsimilarity. It basically says that if you take an image and you take a region of it, you downscale it, and you look for a smaller block within the image, it's very likely that you find something which up to a very high % resembles the downscaled sample. Therefore, our idea is to exploit this to make super resolution. We are going to try to construct a dictionary of examples from the input image. We are trying to analyze the low frequency information and the high frequency information in order to have pairs of examples. And then we are going to make interpolation of the input image, which will result in the low frequency band of the upscale image. And based on the examples that we've constructed from the input image, we will be able to extrapolate or synthesize the high frequency band. So our contribution is a new super resolution algorithm that it only requires one input image to work. We need to have several captures in order to make super resolution. It will, as we will see, obtain the low frequency band of the upscaled image by interpolation of the input data, and we will synthesize the high frequency band by exploiting the former image property. And as a features, well, we are able to apply any rational upscale vector, which is nice for interactive applications when the user can zoom in up to any desired factor. It's an algorithm that is real-time capable. It's very well designed for being used on the GPU, for example, and we introduce robustness against aliasing artifacts. So here we have, for example, a patch from an image where we have applied nearest neighbor interpolation. Then the classical way to zoom in is to apply qubit interpolation that provides something like that. And by applying the proposed technique, we can get something like this. I think you can see some gain in detail and also some nicer contrast in the resulting upscaled image. Well, the method has several steps. First, we are going to make a detection of zones with high contrast, which are prone to contain some aliasing artifacts. Then we will upscale the input image by standard analytical interpolation in order to obtain the low frequency band of the upscaled image. Then we will perform some two-band analysis on the input image in order to generate our database with examples. And then we will use this database in combination with interpolated low frequency band in order to generate the high frequency band. Finally, before combination, we will ensure spectral coherency and we will form the super resolved image. So as I mentioned, we are going to try to detect high contrast regions. We can see in this image, for example, that around the helix of the plane, there's a high contrast region. If we zoom in, well, with this resolution we cannot see, but there's actually quite a high amount of aliasing around this region. And well, with the control detection, we can have a mask signaling where those aliasing-prone regions are likely to appear. The next step in the algorithm, as I mentioned, is to obtain the low frequency band of the upscaled image. We do this by basically by applying an interpolation filter after zero insertion and then applying a decimation. However, by doing so, it's very likely that we introduce ringing in the interpolated image, because such filter is eliminating the high frequency bands, and therefore by that phenomenon, this is going to appear. And then what we do is, while observing that natural images very commonly present an exponential statistic in the gradient, we impose it by regularization, and then, well, we try to minimize this expression by a gradient-based approach. This works pretty fast as long as the regularization factor is small, and therefore it's the approach that we follow. Sorry, I forgot to mention, this is applied for those pixels which are in the neighborhood of a contour point. That's why we use the mask M to signal them. For the rest of the points, we just rely on the interpolation because the amount of high frequency component is small enough to rely on it. So, well, it's important for us in order to keep the cross scales of similarity that the filters are compatible between the analysis filters and the ones that we use for making the interpolation of the low frequency band. Therefore, we rely on analytic filters, as we said, and we ensure that the frequency response is identical in the sense that they have the same cutoff frequency and normalized. And well, this is the shape of such filters. Here we have the spatial response and the frequency response. The high pass filter is just the complementary of the low pass filter, which is a separable filter and can be implemented very quickly with the convolution is separable. So up to this point, what we have is the low frequency band of the upscaled image, which has been interpolated. We have the input image, which is low resolution, separated as two bands, low frequency and high frequency. And what we want to do now is synthesizing the high frequency band by exploiting the cross scales of similarity. So we do this in a block-based manner. We make small blocks of 5 times 5 pixels, which are overlapping up to the point that when we're actually applying a sliding window algorithm, we make the maximum possible overlap. And we have a search window in the example database where we're going to find the best match for each sample of the upscaled low frequency band and the original low frequency band. When we have obtained the best match, we can take the high frequency information, the corresponding high frequency information, and use it as a guess to the high frequency information of the upscaled image. Since we have a large amount of overlap, we actually have a number of estimates of the high frequency for each of the output pixels. And these are reordered in order to have a collection of images that we will use as follows. One critique that we could make to this method is that applied to the CPU is rather slow. We are making a deep search in the search window. I mean, we are testing every single position around each block. But the nice thing is that it is very easy to implement on the GPU, and it's very fast. And this is how we do it. So, as I mentioned before, we have a number of estimates for the high frequency band of corresponding to each pixel. And what we do is, again, we impose a exponential statistic for the gradient of the image in order to avoid the presence of aliasing and ringing and other sorts of effects. We again only do this in zones which are close to high contrast contours. And for the rest of the pixels, we simply average the contribution of the NC overlapping high frequency estimates. The nice thing of having a nice number of a large number of overlapping contributions is that we have a better noise rejection. But one drawback that we will have is that this will introduce a slight oversmoothing. You will see it on the results. Finally, previous to summing the low frequency band and the high frequency band, we ensure that the high frequency band doesn't contain any component in the low frequency band, and then we simply add them together. Now I will show some experimental results. We picked two state-of-the-art methods on single image super resolution. This by Glatner et al. Was presented in the ICCB three years ago, and this is available in the transactions on graphics last year. And well, in all cases we are using times 4 upscaling, and we apply this on a database of 10 images, and we average the results. And as we can see, the proposed method provides better PSNR and also better structure similarity. It's not the fastest approach. The Friedman method is larger, but well, we are still capable of working in real time. Here we can see some qualitative results. We can visually assess that the method is actually working. Compared to the approach of Lasna, we can see that we have less aliasing derived artifacts. And well, compared to the approach by Friedman, we can see that we have a reduced amount of false contours. But here, with a very artificial shape around the VA. In this experiment, what we wanted to observe is the synthesis of the high frequency band compared to the classical approach, the bicubic interpolation. And as we can see, the bicubic interpolation introduces a lot of aliasing artifacts, whereas our proposed method is capable of correctly, or at least plausibly, extrapolating the high frequency band. If we take a close look, this is the result of bicubic interpolation. You can see here some star cases around the edges, whereas with the proposed method, they appear much cleaner. You can see the difference. Well, in this other experiment, we just wanted to compare our proposed method and our proposed method without applying or forcing exponential statistics on the gradient. And as we can see, the presence of artifacts derived from aliasing is quite high in this case. This is some sort of an application example. We have a large panorama. In this case, it's not a video, but a picture, where we might want to take a zoom in. And well, this is the result that we would obtain by using bicubic interpolation, the standard method. And this is the result we would obtain by the proposed approach. As you can see, for example, in the skyline, there's a better definition by our method, and also in those parts where there are more details present, it also looks somewhat sharper. If we zoom further in, this is the result by bicubic interpolation, and well, this is the result that we obtain. I think it's clear that there's a gain in contrast and also in the sharpness of the reconstructed image. So, to sum up, well, we've presented a new robust approach for single image super resolution. We are making an effective exploitation of scale-cell similarity, and well, as a nice feature, the algorithm is suitable for the GPU, and therefore it can already be applied for real-time systems. For the future work, we would like to integrate it in a 3D point video prototype that is under development in our group. And we also want to extend the framework to temporal super resolution. This has already been done actually, it's going to be presented soon. And of course, we would like to make further experiments on the resulting perceived quality, so we could use some of the ideas in the previous session for that purpose. Thank you for your attention.
Maybe still have time for one question.
So try to find in the sliding window, you said same blocks. Yes?
Mm-hmm.
So I think for edges it was relative. But what about corners?
Well, it's a quite similar case. I mean,
difficult to find same corner or block corner.
Well, let me go back to this slide. So, I mean, here, for example, we have a corner.
Yeah.
If you downscale it, you obtain the same structure once again, and you're getting the example only from local search.
So you only have a 10 by 10 search window?
Yeah, let's say this is the block, the search window is something around it.
Yeah.
And then in this 10 by 10 search window, it's very likely to find a good example of the high frequency band.
Okay.
I mean, if you want to check further experiments on that direction, I recommend you to check the article of Friedman 2011. It's in the transactions of graphics. He has extensive experiments proving that this actually works.
Also for corners.
Sorry?
Also for corners.
Yes, actually, there are plenty of corners in the images that I used, and it works quite nicely, yes.